Girl, we found area, perimeter, and volumes of so many things. I just wonder what else we can do with this pie.
Amy girl, let me tell you about this unit circle I just found out about. You can find all kinds of trig functions by switching degrees of a circle into radians by multiplying your degrees by pi over 180. The unit circle, or all 360 degrees, equals 2 pi radians. For instance, if I was trying to find out how many radians was 90 degrees, I could take my 90 degrees and multiply it by pi over 180 to get my pi over 2 radians. Radians are another way to measure angles, and we can use these radians to calculate sine, cosine, tangents, and other trig functions of these angles. For instance, sine is your y and cosine is your x, and on all of the 360 degrees, and tangent is sine over cosine.
Hey, 2 pi radians equals 360 degrees for the whole unit circle. That makes perfect sense, since the circumference or the perimeter of a circle, the formula is 2 pi r, and in the unit circle, the radius is just 1.
Well, when are we going to use this after we graduate high school?
Pi comes up again when you're trying to find the area of a region in the xy plane.
That sounds hard. How do you do that?
Well, if we look at this region right here, when you're trying to find the area around it, you have to take the double integral of it. So first, we have to find the equations of these circles. This circle right here would be x squared plus y squared equals 4 because the radius is 2, and this one would be x squared plus y squared equals 25 because the radius is 5. So if we solve each of those for y, those would be the bounds for our integral when we integrate with respect to y. And then our x values are just 2 and 5 because those are our respective radiuses of our circles. But this is not fun to integrate at all. So there are things called polar coordinates that you can use to make this integral a lot easier. R, which is essentially the radius, is x squared plus y squared. So we know that 2 and 5 are our r values. And then we also can integrate with respect to theta, which is just the angle, the sum of the angles of our region. So if we were to integrate this to find the area, we have to integrate r dr d theta. And so we put 2 and 5, our bounds for r, on the first integral, since we integrate with respect to dr first. And then we put 0 to 2 pi, since our region is a complete circle, and that's the complete angle when we integrate with respect to d theta.
Oh, I get it. Okay, so now we just take the double integral. So we take the antiderivative with respect to r first, since we have dr, which gives us r squared over 2, and we have our upper and lower bounds. So now we plug in our upper bound, and we subtract our lower bound to get this new integral, which now it's from 2 pi, 0 to 2 pi. So we take the derivative with respect to theta with our rules. We plug in our new bounds, which is 2 pi and 0, plugged in 2 pi and subtracted, plugging in 0, and we get 21 pi.
There's also things called spherical coordinates. Polar coordinates are when you're using it in just the xy plane, but if you're using it in the xyz plane and you want to find the volume of a surface, you have to use spherical coordinates. They're very similar in that you have a rho, which is pretty much the same thing as r, and your polar coordinate, which is the radius of a circle. You have a theta, which is the angle around the xy plane, and then there's also an angle phi, which is the angle as you're coming out from the z-axis.
Wow, I'm stuffed. We sure had a lot of pi today.
Yeah, we did. And we approximated the value of pi with the perimeters and areas. We also looked at how pi applies to angle measures and radians, and we even looked at how we can use pi in double and triple integrals.
Pi sure is a helpful number, even if it is irrational. Hey, let's go work on Yasumasu Kanada's record for the number of digits found in pi.
Yeah!